By the way, guys, there were a lot of tools for writing Python code and everything. I like Sublime Text, honestly, because of its color scheme and the fact that it's fast. No matter how big the code is, it doesn't crash, but it does nothing else. It doesn't do any kind of syntax check or nothing really. That's why. So if you enjoy things that are simpler, this is not a bad option. We will use this just to look at Py files later, but that's not used for the first tutorial, which we're going to run, which is this one here. That's not visible. It should make it like a little bigger. Is this more visible? That's bigger. This size? Okay. So I thought that there are, I talked to a lot of you guys during lunch hours and other hours, and it seems like many people don't know how to start thinking about their experiment or their problem, and in terms of how to start modeling them with anything. And I thought that instead of jumping into the more advanced stuff that I was talking about at my talk, just immediately, I'll start with this. If you only take this part out of this and apply it to your experiment in any possible way, I will feel like this has been a very successful day. Not that you need to apply it today. Just if you have any intuitions of how to apply it to your own work, that would be a very good goal. Another goal I have with this one is that you would be able to compare trial and error based behavior versus something that learns values and updates values based on experience, and to be able to identify and tell me how to use learning rates, discount factors, exploration parameters in a reinforcement learning model. And then the next notebook, which we will talk about, and that has successor representation, will build on similar principles here. Okay, so the OpenAI Gym, how many people have not yet installed it?
I've installed, but it's still giving me an error when I try to import the module.
Yeah. If anybody wants, who else has a problem that needs help with OpenAI installation? You guys. What is your problems right now?
Yeah, I resolved it.
You resolved it? Okay, so maybe you want to help those guys over there. I think there is Sev there. He has a problem. Okay.
So maybe I should load this module.
So I just want to give you one example of state abstraction. Guys, do you guys remember Sam's talk? Everybody remember Sam's talk? So the one that you see on the top left is one of his experiment, which is there were two rooms and the rats would come in and here's where the things were. But there's other ways of abstracting that space. So the state abstraction that, for instance, Bob was showing us, this is what we can do to Sam's experiment. Just so you know, that experiments that can look like this top left image, they can be, you can do state abstractions over them, even if it's your own experiment, and turn it into things like this. The one in the middle is the trajectory the rat moved, right? So this one all of a sudden looks like an H. What looked like a box can look like an H. It can look like this tree. It can look like this tree, depending on how you do the state abstractions. So when you think of your experiment, don't think that it needs to have been designed with reinforcement learning in mind for you to be able to analyze it with that. Afterwards, if you're interested, come talk to me. Experiment into a version that has a tree and has an MDP, and we can think about whether you can use it on it or not. So keep this in mind as we go on. In spite of differences you will see between these designs and your experiments, doesn't mean your experiments can be abstracted. Just this was a sideline for another thing you might want to learn. Okay, so does everybody, who doesn't still have OpenAI? You guys still don't? Why don't you use Colab instead? Google Colab.
Wait, if you're having trouble, maybe
TAs will help you. So another option. It's true. Wait, I should keep my voice down or no? Okay. I don't know. Sometimes I'm very loud, so. perfectly, yeah.
I will note people that the second
Yeah.
second cell, if you're having trouble with it, there's a typo in it at the very last line. So the dot, there shouldn't be a dot there after n. It should just be n. Because I don't think it'll work on any computer as if you try to execute that code in the second cell.
Yeah, correct.
Oh, you mean this one?
Yeah.
Yeah, sure. That's, yeah. That actually doesn't need to be there.
Cool beans.
Yeah, guys, in case of doubt, common sense is always a good, yeah, so it could be that sometimes I deleted something and not the whole line wasn't deleted, so something is left. If you notice something like that, it's a good idea, just shorten it to just say it to the rest of everybody else. So. Okay, everybody on board-ish? Yeah? So this is a taxi problem that we're going to get out of the OpenAI gym. This is an environment that has like a bunch of different environments, and they all have a similar structure when you want to extract them. The environments will have some kind of a problem. In this case, there's a taxi. You can think of it as an algorithm for a self-driving car you want to write. And what it needs to do, it needs to pick up someone and then drop them off somewhere. But initially, it knows nothing about who and what. One strategy it could use is to just randomly move around until it randomly hits the right pickup spot, and then randomly moves around until it randomly hits the delivery spot. So when you do complete random exploration and don't learn from your experiences, let's see what happens. The cars, this is a grid world, so you can see what it looks like somehow here. It's basically, there's 4 different spots. One of them is pick up, one of them is drop off. The car starts from a random spot in this maze. And then the actions that it can do, I've copied it here for you guys. It can move south, north, east, west. It can pick up or drop off. And that's it. Those are the actions that it can do. It received $20 for dropping people off, -1 for each action. But if it does some illegal moves, then it gets a -10. And you can sample all of these things from the environment parameter. I just want to highlight that the room's acoustics are such that, yeah, I hear like a lot of your conversations. Your voice is low. Okay, so here's the first part. So let's try something simple out. Let's just load this. So if you guys run this line, basically, you can just run it also in a different cell. Did everybody try that? Okay. And this end.s, basically you're telling it where to initialize your random state. You can put it at any number you want, but it shouldn't exceed the number of states possible. And then here we're saying how long it should be able to run. We set the penalties and rewards to 0 because it hasn't done anything yet. And here, let's try a very simple algorithm. We say until you drop somebody off. So basically forever do this and only stop if you drop somebody off. The action would be sampled randomly from all the possible actions in the state that you're in. It means I'm not making any choices of my actions on the basis of the fact that I've experienced this action has been rewarded in the past. I'm just randomly taking any action from that state I'm in, okay? And then this is this line that is over here. Then we say, all right, end that step by this action. And what it does is that it gives you where's the next state you land in, what reward you get there, whether you're done or not, whether the whole thing is over. And also, it gives you some extra information of what happened. Now, what you got? If your reward is -10, that means your penalties should be added because every step that you take has a cost of -1, but there are some penalties, and that's you want to add to that. And then at the end of this, we run this. Basically, this will run until you pick up somebody randomly and drop them off. And then we can print how long it took. Let's run this still a couple of times to see how long it takes. First time, it took 2,860 time steps, and it got 939 penalties. Let's run it again. This time it's 8,500 time steps, and a lot of penalties, like 2,600. This time it's 800. This time it's taking longer. Did I accidentally run something else? No. This time it's 514, and the penalties are 160. So what you notice if you run this many, many times is that you can't predict how successful it will be, how much penalties you will have, because it's not learning anything, right? Now, to get a better idea of this, I'm basically copying the same code you saw above. The only thing I'm adding is that I'm saving every frame of what happened in that time step, so we can make a little animation down here. So the only difference in this next cell is that we are saving the frames with the rewards that were saved, so later we can make an animation of what actually happened. Now, this is going to take a while. If you're ready, you can run it on your own, or you can watch the one on screen. It's going to take a while. But you can see the yellow is the cab. The location Y is the pickup point, and R is the goal state. As you can see, I think so, yeah. And as you can see, it's, okay, randomly went there. It's like not figuring out what to do, basically. It's very frustrating to look at something that's moving randomly because you kind of want it to be a little more strategic in its search. You can imagine how, you can see that the algorithm is not a good search algorithm for where to go, or a good exploration algorithm. This is what random exploration looks like. Bob Wilson is a world expert on random and directed explorations, if you want to talk to him afterwards. We're going to wait until this is over, I'm sorry. Hopefully this is not an 8,000 one. Just just different locations that it can drop. So the 4 corners are the locations that you can pick up or drop off. In this case, the pickup location is B, and I think the drop off is R or something. The colors indicate what's the, and the yellow is the cab.
Sorry, can it move like up to any border? Can it move?
Unless there's a wall. So there's illegal actions. It can choose, the random action it chooses is from the legal actions. This is so annoying. You see, it was just there. It keeps going back. It's not. Did anybody who run it on their own cell end? Yeah, yours ended, yours ended, yours. Okay, you guys are the lucky ones who got a shorter trial. I'm hoping this is not a 8,000 there, because then we will have to just manually stop it. Can you imagine while you're sitting there, what would, in your mind, can you imagine what would have been a better strategy for exploration here? Like keeping track of something, learning from something. You can think about it, right? Just like watching how bad random exploration is.
Is it also taking random states, actions at each place? It's not just like going to different spots, it's also like at each spot it's trying a different random thing.
You can answer that question by looking at that loop and tell me the answer, actually.
Yes, it's literally sampling the action space totally at every spot, so it's trying to pick up empty space even, like, and drop off at empty space even when it has nothing in its.
It's not that complicated, right? It just takes random actions at every state.
Yeah.
And because of that random action, it will end up somewhere.
Right.
And then it will take a random action.
Right. It's just that some of the actions just seem illegal in a sense, right? Like I can't be in a taxi and pick up. I can't take a pickup action for like if there's no passenger there.
So one thing you can't, oh, did it end? Yay, okay. This was lucky, it's the 1800, yeah. Everybody ended or some people are running? Okay, probably some people are still running. But as you can see, finally it got like 20 bucks, but then it had a lot of penalties that actually I didn't print here. I should have added the penalties so you could see. But yeah, it's safe to say it had a lot of penalties. And it took this many number of time steps. Okay, if you just want to see the value of each frame that it was exploring, you can also explore it separately like this. So this is for frame 1. Let's say I want to see it for 101. This is the value of that and everything else. So you can actually look at them separately. Now let's try something with Q-learning. And how many people remember from Kate's talk and can tell me something about Q-learning? Who can't say anything about Q-learning, which you learned anywhere in your life?
Like updating the value based on the difference between the real reward you get and the expectation.
Exactly. And a part of this tutorial when I wrote it last night was that by the end of this notebook, if one of you or some of you could come to the board and write the equation. Kate had the equation on her slides, and there are cheat sheets there. But exactly what Mingyu mentioned, if you can at some point come and write the equation, that would be great. It's very simple. It's just a mnemonic for mnemonic purposes to ask somebody to come and write it. That's it. So what Mingyu said was that you experience something and you update the value of what you experienced on the basis of the outcome that you observed of the action that you took. Okay? So every step that you take an action and make some observations, you update the value for that action, right? Let's see how we can do it here. So there is a table that you save basically of values. So we call it a Q table. What is the difference between reward and Q values? Does someone, what's the difference between reward and value?
Values you estimate over time. Long-term estimate.
Right. Reward is what? I mean, it could be 1 times step 2, but broadly, it's not just one reward, right? Now, what's the difference? So how many different ways could you estimate value? Like you could just sum everything that you had seen and have no discounts. You could imagine that you put some weight and experiences or predictions that are closer to you will have a different value. You could imagine that you use a model to predict what's going to be the future value of something with that iteration that we mentioned. So you can do value estimation also with a model-based approach or with a success representation-based approach or with a other version that you have some kind of a representation of your state space and you want to combine that with the rewards, right? So generally, rewards are exactly what you experience at that moment that you're receiving the observation, but value is something that you estimate and not necessarily just over time, but just, on the basis of other factors that you're taking into account. In this case, does Q-learning have a model or a cognitive map? Can someone answer that? No. So it's a model-free approach. It can be combined with other representations, but in this case, to have a hybrid model, but in this case, it's just model-free. What does that mean if something is model-free but still estimates values, and how does it do that? Yeah?
There's no transition probabilities?
No, there are none, exactly. Well, I mean, they're in the real world, but it doesn't keep track of them. So what does it keep track of?
Past.
What kind of past? Or what things about the past?
Values from the past, the rewards.
Yeah, so like a running average. It's just like, within this past weeks, this is what I had, so probably next week's, within the last days, this was not bad, so within the next day, it's not going to be that bad. So it's kind of like very based on keeping track of a running average, right? And here, the Q table that we're defining is something like that. As you can see, that it's currently we're initializing it, so I'm adding here using NumPy. The number of so I'm just making a matrix or a table with just zeros currently. And it has observation space, that's the number of states in the size of the observation space of this environment and the size of the action space of the environment, which just means how many states and how many actions you have, right? Because you want a state action value. And and then there is this alpha, gamma, and epsilon. And maybe some of you already know what each of these are. If you don't, by the end of it, I would want you to, as we are going through the next lines, keep track of what's happening in every line and try to figure out what these values are. And then we will talk about them. Okay, let's run this. And of course, you can at any point change these values also. All right, let's write an action selection that is a little smarter than the one we had before. We're still not going to throw away exploration entirely, although you could. And I think here you might realize what epsilon is out of those 3 values that we were talking about. So the model is very simple. It takes an environment and an epsilon value. It draws a random number, and if that random number is smaller than epsilon, then it will take a random action. Otherwise, it will take an action based on the Q table that is maximizing value. So it chooses a greedy action with probability 1 minus epsilon. So can someone tell me what epsilon would relate to based on what you're seeing in this? Yeah, exactly. So the smaller it is, what happens?
The smaller it is, you explore less.
Exactly. And if it's 0, then you basically never explore, and that's when you're greedy. You're just constantly going for the best action, according to what you've learned. Okay, let's run this so we have that function. Okay, now we can try our taxi to be greedy, learn things, and remember good actions while exploring just a little bit, as much as epsilon. Yeah.
Like a question about this environment.
Yeah.
Is the state represented so that you get different set of states when you have passenger? Or is it like, how do you know if you have passenger or not?
There is no difference currently. It's just you're a taxi driver. So this, yeah.
Okay.
You're a taxi. The agent is a taxi. We don't have a passenger.
But you were supposed to pick up, oh no, okay, you get points directly when you pick something up.
Right, but pickup is just the action that you do in particular state.
Right, okay.
So it's not that another agent gets added. That's a good question, actually, because the example might be confusing. It just ignores, imagine it's a package is picking up or something. So it's just that there's only one agent, and that's the taxi.
But you don't have to pick up something before you deliver it.
You do.
So then you have to keep track of if you have picked it up or not.
Well, okay, I'm very glad you mentioned that, now that I understand what you were asking. This is exactly the problem the paper that was proposing this example wanted to address. So if you scroll up, I have linked to this paper. This paper wanted to highlight the problems in hierarchical reinforcement learning. And this particular example of the taxi is exactly because there are sub-goals and there's hierarchical states. So we won't talk about it today, and that's partly the reason I chose this example, because although we can compare how much better Q-learning is, hierarchical reinforcement learning is a serious problem, and Q-learning is not the optimal answer here. We will talk a little bit about how best to address this, but I think you might already, based on your question, you might already have an intuition that even Q-learning might not be the best, because it's not keeping track of states. So you already are way ahead of me in this tutorial. Did everybody understand this concern? If a particular, although we are comparing trial and error versus Q-learning, as we mentioned many times, Q-learning does not keep track of states. So how do you know if you've already picked up or not, right? There is a particular way that here it can learn based on a sequence, right? So it doesn't need, in this case, to keep track of states per se, but there are problems there. So yeah, there are many branches of conversation and thought that can come out of this, what we're talking about. It can learn based on, I went there and then I went here and I got rewarded. So I'm going to keep doing this again. Oh, and I'm going to keep doing this again. So it can learn and keep track of the sequences if it has a gamma large enough. Okay, so where are we? Which line were we? Did we run this yet? No. Okay, so now let's take a look at this code, and we're going to run it in a second. Does everybody know what TQDM does, just in case somebody doesn't? There are different ways to pronounce it. Some people say takatem because it's based on an Arabic word. No? It does this beautiful timeline here that it just it's a bar. It tells you how many rounds of a for loop you're doing. And you simply import it. You say import TQDM in the beginning and then add it with a parenthesis in the beginning of whatever for loop you're running. And it makes it easier for you to keep track of how long more your cell is going to run. And I've noticed that a lot of people get frustrated when they don't know how long more to wait. So it's a very simple solution to that. Everything else should be kind of old school. Nothing special is used here. So Q table, we kind of store it. We decide that we want to train for 1,000 trials. In this case, we of course want our agent to learn from its experience. We do the same thing, so we reset the environment. Remember last time I put the S to something? Another way to reset the environment is just to use the reset function. There are different ways of doing it. And then here, just set everything to 0 again, and while not done. So we do a very similar thing to what we did before. Can someone tell me which lines are different between this? Just intuitively, you don't need to look and compare. Between this and the random approach, what's changed here? What's the part that's different?
Select action.
That's the part that is a bit different. What else is different? Because before we used to only randomly select action, now we wrote a function that actually uses the Q table. What else is there? Yeah, the value update is the key change here. And remember that Kate was talking about kids actually having sometimes good some kind of model or representation of what's the right thing, but not using it. The model itself is one thing to learn, or the table or something. Using it in your action selection is another thing. So you can here see between these two differences, between this and the other trial and error version, that it's one thing that you're learning representations, it's another thing that you're using it in your action selection, right? And we have added both of them to this one. And that's the only difference from trial and error. All right, can someone explain what happens here in this value updating? I'm just gonna make it clear that this is an important line. This is basically the line that at the end you would wanna like write an equation of, and this is the equation you see when people talk about Q learning. So this is like the key sort of equation here. So and then of course, like we add 2 penalties if that happens. And we just save the frames here. All I need is if someone explains this part to me.
So you look up, the current Q value that you've got, and basically say that your Q value in like time point t plus 1 is the old Q value multiplied by some sort of learning rate. So that's what's represented by alpha, or by 1 minus alpha in this case. And then you add that to your projected award. So that's alpha, which is again learning rate times some sort of summation of expected reward. Not exactly sure what gamma is. Maybe inverse temperature. Is that what it is here?
Discount.
Discount. Okay.
What does that mean?
How much you are like discounting future states, so how much you're prepared.
What's the range of the gamma value? Exactly. So the smaller it is, the more myopic you are. As Kate was saying, the larger it is, the more into the future you can sort of estimate your expected value. So what is expected value? It's exactly, whenever you hear the word expected in reinforcement learning, means exactly how far into the future are you sort of anticipating the future of a state you're in to be. So the expected value of the current state includes what I expect to receive from future states that follow the state with some kind of discount. Yeah?
It seems a little unfair that you take the max over the future states to represent expected value, because there's some epsilon, right? There's some randomness to your choice in the future too. Does that matter? Or is that
I don't know, you tell me. What is the Q table trying to store?
the values associated with all actions in all states?
So if we say next max and we want to see what's the best value of the next state, we don't know which action you're going to take, right? Q is just saying, if you were greedy, this is what you would get. And in your action selection, if you're greedy, you take that instead of taking the random. But why is it still useful to take the random, especially early on during learning?
You're not sure if you're stuck in like a local.
Exactly. It could be that your best estimate of the max of the future is not really the max, right? So you're always looking for the max, and by adding the max there, you make sure that in your iterations of this, many times that you will experience and sample the world in different states, you end up with the best value, basically. So this is written in a way that is masking the actual equation you will be writing on the board. Just so you know, this is not the equation you will be writing. There is there is something called the prediction error that makes a different way of writing this mathematically or in terms of equation. Can you guys see that? Can you see how this can be expanded in a way that you can get the prediction error separately? You don't need to see it now, but think about it. Think about it by the end of this notebook before we move to the next one. Okay. On everything else that you see here is just about saving the frames and honestly just cleaning the output so that we can have a nice plot. So I'm just going to shift enter and run this cell. And as you can see, we can see that it's running. This is like it's running 1,000 episodes. And here you can see, as you can see, we're in episode, that was 420, 617, 820. It's going very fast. Now it's done. Now we have this figure. Remember some figures I showed you from the Sutton and Bartow book? Those were figures from the 90s with the grid world. This is basically a figure like that. So who wants to explain what this figure has in it? What was a training episode? Does anybody remember what was an episode? I mentioned it in the talk. And it was written, honestly, in the notebook, but I didn't say it today. Exactly. Going one time where you went from start state, took a bunch of actions, and reached reward, that trajectory is one episode, right? What are you seeing here? What is an epoch? Or number of epochs, what does it say?
Is it just number of steps the agent took?
Exactly. Within every episode, from starting to end to reaching reward, how many steps did the agent take? Now, what are you seeing in this graph, basically, in this plot? How is this plot showing you that the agent is learning, or how fast? Yeah?
Yes, it's learning over time as a function of time because it requires less steps to reach the goal.
Exactly. Okay. Now that we've done this, we can now compare it to what we saw earlier with that random actions. So let's run the random actions for 1,000 times just to be fair, because, the rival company deserves to give their car also 1,000 experiences. We all know they're going bankrupt, but still, let's give them a chance.
Is there an easy way to plot the Q values on top of the grid?
That is a great project for you to do, yes. You can look in, depending on which plotting you want to use, whether you want to use Matplotlib or Seaborn or whatever, you can get that value and incorporate that in your color scheme, for instance.
But there's not just a super good
You mean?
as part of the environment.
The environment is not a reinforcement learning environment. The environment, it just gives you the agent and the environment. It doesn't give you analysis tools. So everything, we're writing them right now. So why don't you write that? It's not a bad thing to have. It's always good to have your own little preferences as a side pie. And you will see that, for instance, I made my own environment, so I saved some stuff there and everything. You'll see it in a bit. Okay. So now here we compare the yellow, random guys with the blue Q-learning taxi. You can see the scale. This one went up to 10,000 epochs per episode. And as you can see, there is no trend. It's not getting better. Is it getting better? It's not getting better. Randomly, sometimes better or worse.
Sorry, in cell before, I was confused because, so in the immediately preceding cell, you're plotting the previous all epochs.
Oh, sorry.
It's
Yeah.
all epochs.
I needed to plot this one, all epochs ran. So I can plot it in another cell. Insert cell below. Here. This is the one. So guys, just fix this. This should be all epochs ran, but if you run the whole thing around the one, it doesn't take too long. So you can do that too. And I can do this, so you can also see this in yellow. So this is the all epoch strand. And so by chance, we now have them next to each other here too. So that's not bad. And here, as you can see, this is maximum 1400. This is maximum 10,000. So when I plot them on top of each other, you can't even see how much improvement you get from Q-learning. So I'm plotting them next to each other to see. So does this give you an intuition of how you might be comparing different learning agents and potentially using them for your own task, I hope. And if you want to try things on your own tasks, talk to me. We can see how we can do an abstraction of it if you just want to use something simple. The next tutorial I'm going to go into is what I initially wanted to do. So it's a little faster and it's a little but hopefully because of this one, you will be better able to follow. I'm not going to go line by line like this one, but I'll tell you what are the key parts where you might want to explore further. And these are the questions you should be able to answer by the end of this. So read them, think about them. If anybody wants to come to the board and write the equation for Q-learning, that would be awesome. Anybody? Any? Mingyu? And then you can compare this to that line that we saw up here and see how I wrote it differently so that you can't see it just by copying this. But you will also see why it's easier maybe in the code to write it like this, hopefully.
So it would be, you've got Q value is for your, I guess you're like updating it from, this is like your Q value from the previous time step. And let's say you are currently in state S, and you take an action. I'm like making this up. So you update this is your old value. So alpha is the learning rate. You multiply alpha with the actual reward you get. Plus, if you consider you're gonna look ahead into the future, so that would be you take max over all possible actions. You put that. Minus your so this is when so you're currently in state S and you take an action A and you transition into a new state S prime. And at the same time you get a reward, which is RT. So you update your value. So this is what you expect before you take an action and get any outcome. And this is what you actually get plus your expected value of the future and discounted. And we talk about it, wanted to take the max because that's sort of the best possible future you could get, I think. Is that?
Pretty much, yeah. There's only one thing. Where does this get stored?
In the program?
No, in this equation. Where does all of that get stored? Where does Q of t get updated or Q get updated? So you can represent time in two ways, right? You can have t or you can have like the next state or something. I feel like that might be a little off, but do you think you have a... So we don't need the t's basically, right?
Yeah, if you think this is like after taking.
Because you're keeping one Q table.
Right.
You're not keeping different. Yeah. What you're doing is a little more complex because you're keeping like a temporal snapshot of your different Q tables.
Yeah.
And you're only,
we're
it's,
updating the ones.
we're updating the one Q table. That, yeah. Yeah, however you want to write it is good. Yeah, however you want to. They're both correct. Does this make sense to everyone? Yeah? And what she was doing was actually a more complex thing where you keep a track of like your past memories of the Q values too, but like we're not doing that here, right? So the one that you saw there is like an expanded version, just by, or like just a modified version by just 1 minus alpha, but it doesn't make it clear what is really going on, right? Can someone tell me where in this is the prediction error?
It's the last term, right?
Exactly.
The max Q minus the
Exactly.
expected Q from the original
Yeah.
table.
And that's the one that you couldn't see it in the version that is in the code. It's not clearly separating the prediction error. Another way you could rewrite that part and make sure that it works is separately compute a prediction error and then plug it in and write it in that way. So that's a good way of practicing it so you can deal with prediction errors in the right way. Okay, so honestly, if you ever apply this kind of thing and if you feel comfortable with this after this workshop, I feel happy. But I really want to show you the SR and the SR Dyna approaches. There we are not going to go as slowly as we went with this one. But if you get like completely confused, and let me know if your fight or flight is getting activated by confusion, just speak up. Okay, so this is the first one. This is the SR only notebook. There are 3 notebooks in the GitHub repo that I sent you. And in this one, also my tone is different because I wrote the other one yesterday. This one is a little more short and it doesn't explain as much as the other one in the text. So yeah, so you run these things. You will find that there are some things here, some dependencies like IDA-EMS and SR no action. These are classes that I wrote. And these are all in your GitHub repo, so you can open them and see. So let's take a look at the IDA-EMS thing, just so you have an idea. Actually, it might be open in my... Yeah, I think it's open. Okay, so it's right here. So you can see how I'm just like finding a simple way that is comfortable for me in that code, and you can define however you want to just explain the environment, right? And then from this IDA-EMS, I can evoke these things. I can generate example for a bistro or env1. I can plot it. So for instance, the question that Kate was asking, as you can see, I've added a plotting function already in the env, for instance. You can add your favorite version in your RL code. You can turn half of the other notebook into a separate code and call them so that you just have a one-liner for learning instead of all that efforts that we took. So there are different ways to deal with this. Another thing that we would call is this one called SR class NatHum X1. And that's another one that has some functions that actually has a lot of, this is another one. This one. It's this one. I've added some comments so you can see what are the main things that are happening here. The most comments are in the beginning. And the rest, you will see that it's very short functions that call other functions. And you will see them as we go along the tutorial. So I don't need to explain everything before we start this. No, this is SR only. Okay, so let's start with plot env. And another thing that you can do, oh, I didn't run this one. We have to run this first, so it actually has them. Then you can run this. And having seen this is the shape of the abstraction of the experiment that it made for us. You see this here? And if you look in the Nature Human Behavior paper, I have a table there for the differences between model-based, model-free SR learner and hybrid SR. What we saw before was this Q learner cached value. What we're going to see now is the SR learner, and the next one is going to be SR dyno. This is what the experiment really looked like, if you want to look at that, and the results and then the predictions and everything. And then this is the abstraction that I showed in the talk, so everything is in that paper and it's in the comments. Okay, so now here we're just going to train an SR. So before we go into the details, just know that as you can see here, I'm evoking generate nature human behavior, experiment 1 environment. And then I'm feeding that into this other class that I wrote that we will get into after this. I'm defining a gamma and alpha. And then it can run it and show me the successor representation for this, right? The rest is just like text. So what can you tell here from this matrix compared to the stuff that you saw in the talk? What is the key thing about the successor representation as opposed to probability matrices that you can see here?
Like fading representations as you go further into this.
Great. Just the fact that we have multi-step dependencies, right? In the other one, we just had like one-step dependencies. In this case, we actually have multi-step dependencies, right? Which is, for instance, this one, which is a multi-step. Now here, what gamma did we give it? We gave it 0.2. Let's see what happens if we give it a 0.6. What happened now? Do you see what happened? Can anyone tell me what happened compared to the one before? You have a higher expected occupancy of states that are further away. Before, the expected occupancy of states that were further away were way smaller than the state occupancy of where I am right now. But now that I have a gamma of 0.6, you can see how much further away it is. Let's increase it. Let's increase it and see what happens with a gamma of 0.9. Look at this. It doesn't care about short term as much anymore. It cares about the end game, right? So from this state 1, sorry, this is Python that starts from 0. This is not a 0th state, this is the first state. From this state 1, what you see is that the highest value that you have is the last state that you can go to. So basically, if you're planning hierarchically, again, coming back to the question that Emil was asking earlier about the taxi. You can imagine how having applied such a thing to the taxi with a different scale, you could have gotten the sub-goal, which would have been a state in the middle, and then gotten this one with a higher gamma. You see that? So you can see the connection between why I gave you a taxi problem, which is a hierarchical reinforcement learning problem, and how potentially different scales of a multi-step representation can easily solve them, right? So if you have a multi-scale SR representation, you can get that. Now, let's take a look at how long it takes. And for this, we're just going to do it with a lot of alphas and a lot of gammas, and then compare how many epochs per episode it takes in general, how many episodes it takes to reach convergence. We talked about epochs, we talked about episodes. We didn't talk about convergence. Does anyone know what it means to reach convergence, or for our model to converge, or a learning to converge? Does anyone know what that means? Does anyone want to guess?
I imagine it's that at any given iteration that you do it again, it doesn't change beyond some like small threshold that you set, right? So like if
That's exactly right. Yeah, it's not even a guess. To the dot, it's exactly right. So if you look at the errors that you have, or how much improvement you can get by every step that you are increasing your learning, there is a point where you're not going to get better, right? And at that point, you have reached some kind of convergence. And this is important because some of these equations analytically are just like very tough, and some of them are not tractable. But with this learning approaches, when you iterate, then at some point you're like, I can't do any better than this, thanks. So you can just stop at that point. So what we're going to see now is with different learning rates and different discount rates, how long does it take to reach convergence? Does that make sense to everyone now? All right, let's run this, and then we're going to plot it in a 3D way. And some of the dependencies that you had in the first cell were for 3D plotting, so you might need to install that if you didn't have. Does anyone have any problem with that? Did anyone have any? Everybody was good with it? Great crowd.
Question about the successor representation.
Sure.
When you have like a second, the middle state? It's like, it seems like 0.
It's not 0. It's above 0. But at that scale, it doesn't care much about that, partly because we have to open the algorithm to look into it. One thing you can do, and I recommend that you do, compare that to if you did I, identity matrix, minus gamma t, t is the probability matrix. Compare the version that you just saw, which is a policy-dependent version, because as we will go through it, the agent was learning it step by step. Compare that to 1 minus gamma t, and tell me what the difference is.
So if it's 1 minus gamma t, then you would have, I guess, very high, even higher than the last state.
Take a look. Let me know. It's very easy to do it. Just make an identity matrix that's 6 by 6, right? And then minus gamma times the transition matrix for this 6, which you can find in the env. Or you can actually get it probably env dot, you can get it, env dot t, I think. Actually, I might have computed it up there anyway. It's in the other one maybe. And then compare the two. Let me know what's the difference between them. Okay, did everybody run this? Did anybody have a problem? Okay, we're gonna do the 3D. So when you run the 3D, this is what you would see. Anyone got this 3D figure? Cool. How many people didn't? Did you try, or did it not work, or did it, what happened?
I have problems with graphics.
Oh, yeah, some people have difficulty installing that. Did you have problems with installing it, or?
Installed fine, it just says that the module doesn't exist, which is categorically false.
Oh, did you,
But I'm using Conda, so it's part of my virtual environment.
So Jay, you have to install it in that Conda environment,
I did.
and then sometimes there's like a Conda, what's it called, Jay? There's something where you can get your access to your Conda environments in your Jupyter, so you can switch between Conda environments, and there's some package, I can't remember what it's called, you can install. It's like ND Conda kernel or something like that. You can probably just Google it, and then you can swap between them. But otherwise, it installs it to the main one, or you have your main one running and not your Conda one. That's my guess.
okay,
You tried restarting the kernel, Jay?
Yeah, I did.
Just leave graph this as a new path.
It is.
yeah, Graphiz is moody. This has happened before. How many people still have problems? So I know Jay has a problem. How many other people have problem with Graphiz? You have the same problem? Can the RAs maybe, TAs? Sorry, I know. So sorry. Rewards are deterministic.
So why are people not? So if rewards are deterministic, is the optimal learning rate? And why is that? Doesn't seem to be like outcome.
We gave it the learning rate, right? Alpha is the learning rate we gave it.
But I'm just wondering, it seems like the discount factor is mattering a lot.
In this case, it does, yeah. The particular way that it's learning is the case, is the reason that that's the case. And I think that it's time, because your question is related to Mingyu's question. It's both related to the fact that this is a policy-dependent learning algorithm. And we can go inside and see how it's learning. So at some point when everybody's comfortable, we can go inside the SR class thing and take a look at how it's learning. Yeah, so this is just like other fun ways to plot this. There's nothing new in this one. And we're going to compare it to the version with SR Dyna later. But at this point, I think it might not be a bad time to take a look inside or under the hood and see. Let me see what's the right line so you can, this is not bad. Okay. So for those of you who are asking these questions, take a look at this. First of all, I want to highlight that this is a no action version. So it's, oh, ugh. Would that work on this?
Yeah.
Wow, I've never done this. It looks weird. This is like,
Yeah, that's what all the YouTubers do when they want to show code.
oh really? Okay. YouTubers is a good adjective. Now you can't see the rest of this, so I'm just gonna.
This SR information
Yeah. This is SR Dyna No Action. You can see the name up here. So for those of you who are, so this is how the states are being learned here. So notice that there's something similar to the way that we were doing Q learning, right? It's not entirely different. We have the 1 minus alpha of m. The self thing here is because this is a class, so don't be bothered by it. It's just a way of writing a class so it's easier later. So, and then, so basically it's alpha times m. M is the successor representation of S, and then alpha times 1 hot of S plus gamma times m of nu. Okay? Can someone explain to me what this means? Just unpack it. Just basically just verbalize your thinking process of what's happening in this line. So in this line, I have entered I'm in this state, right? And in this state, I had some kind of a successor representation before in this state. Now I'm having but I've arrived again in this state, right? The whole point of successor representation is how often I'm going to end up somewhere. So every time I'm going to end up somewhere, I add, with some learning rate, a 1 hot for that state. What does 1 hot mean? Anybody? And 0 everywhere else. So if you have a matrix or whatever of states, and this one, everything is 0, and this is 1. This is 1 hot for 3, state 3, right? Does that make sense? For instance. And so everything is 0, and 1 is for that state that you're observing. So you add that with some alpha. So it's not exactly 1. It's alpha times 1. Plus the m, or successor representation of this new state that you're entering in. What does that mean? What is different between this and every other time that we saw some representation related to the new state? Before we had Q value, remember? And it was averaging the future of that based on its experience. What is this one? It's, yeah?
It's just occupancies, right? So it's not nothing to do with value by itself, which is occupancy.
It's occupancy, but for how many states? We don't know. It depends on the gamma. So in something that the gamma is higher, you will have more of its future. And in something that the gamma is lower, you will have less of its future. Now, Mingyu, you might be able to tell with a low gamma and a high alpha why what we saw happened. Sorry, with a low alpha and a high gamma, what happens to the middle state? And when you add that middle state, the 1 hot is only with this alpha, right? But then the gamma is going to go further into the future. So the effect of the future would be higher. Does that make sense?
You're raising your current when we considering the future.
Yeah. So the end states are going to matter more. So if you're learning slow, but you're seeing very far into the future, so your representations are going to be skewed towards long-term future. It's going to be the opposite of myopic, right? Which maybe makes it clear for you guys, SR, successor representation with 1 scale, is not great. It's either myopic, or it's middle, intermediate, or it's, or it's like, not dystopic. What is the opposite of myopic? Farsighted. So what could be the solution that I already mentioned in my talk, but what could be the solution? To have multi-scale SR. To not store just 1, but multiple ones of them. And when you want to solve a problem, Mark Howard and I have a paper that's entirely about how to use multi-scale SRs to reconstruct a sort of time series or to estimate distances between things and such. 5 minutes? I think we're good. Okay, so I think you got the main point of all of this. Everything else that you see is in the service of that one line. And that one line is the difference between this approach to successor representation learning and the approach that you will see that is if it was not going towards a reward location, but it was just either doing a random walk or you were analytically first having the probability matrix T, transition probability matrix, and then doing I minus gamma T for your version inverse for computing SRs. This is different. It's policy dependent. The agent is going some places more than other places. It's dependent on learning rate as well as gamma. It's not just the gamma that determines things, and the interaction between them could mean that the learning rate doesn't matter much. Kate, to answer your question, which was very related to Mingyu's question, in fact. And so it's a different kind of story. And you could imagine that for different environments, depending on the kind of experiment you have, the kind of volatility your experiment has, the kind of time scales that matter to your experiment, different kinds of learning scales and discounts might be optimal, right? I'm just going to because we don't have a lot of time, I'm just going to, and I knew this was going to happen, that's why I wanted to stress on something that you can take away. I hope that the Q learning really got home. So this is the third notebook. Everything is very similar to what you saw in this notebook. The only difference is that it has that replay. So if you remember from my talk, the prioritized replay that I showed you in the algorithm, this just adds that. And we won't have time to go into it, and there are many different ways to do the prioritized replay, and I have just done only one of them in the version that I've given you. And the only thing I want to show you is if you come to here, you can see how much faster everything is learned with the same gammas and with the same alphas. And the reason for this is that for every time that I'm getting some experience, I'm replaying this a bunch. And extra points to whoever goes inside the code that I'm using for this and tells me how many times unless I identified it here, I hope not. Yeah, I think, yeah. If you go in there and tell me how many times things are being replayed and then change it and see how things change based on that. So we can basically now compare the two. So this was our old one. This was our SR alone without the replay. As you can see, sometimes it took it 175, 200 episodes to converge. But as you can see, this little guy here, the SR dyna, just by adding replay, is pretty low. And if you change change your replay parameters, you can get it even lower. So that's another advantage of adding replay to whatever model you have. You can compare it to the other models that don't have replay by comparing how much more. And also, if, I don't know, those of you who work with rodents, if you're, I don't know, giving them rest time or damaging their replay by disrupting their ripples at some point or turning on and off something in their brain, you could basically simulate that also by changing the algorithm of the replay or whatever it is that you're doing to the rodent. Yep.
So there seem to be two parameters that are called. So replay steps is 1,000 and n samples is 50. Is replay steps like the number of steps back that you're redoing, and from that you're just sampling 50 random ones from the last 1,000 iterations?
Yeah, what else is there for the recency thing? There's one more thing. So you remember by the way, guys, the one of the figures that I was showing to you from Sutton and Bartow book was comparing 5-step planning or replay versus 50-step planning. So 50 is common in small reinforcement learning. Another thing is if you replay things sequentially in like sort of a sequential batch as opposed to randomly, and that makes a huge difference. In this case, because of the SR, we're never really replaying just one because it's having the whole future when it's updating things. But in methods that don't have this multi-step approach and their replay is just one step, they don't learn dependencies using the replay that are far ahead. And that's one of the critiques of the early Atari deep learning algorithm because it had replay, but it was replaying random states. So it was helping with games that were shooter games or River Run, which is a plane that just has to, fight off whatever is on the screen. And what they had done was that they would collapse 5 frames onto one another to see what happened to the outcome of the action. And this approach worked very well for those games that were fast-paced. But for games that had longer time scales of anything happening whatsoever and had very sparse rewards, like Montezuma's Revenge, that was a disaster. It was just like not working. And a lot of every AI conference that you go to, there's always a paper or two. And like at the last AI conference, one of them won an award, which is just finding other ways to solve Montezuma's Revenge. What was the last one we were at? ICML. One of the papers that won an award was one that was comparing different approaches to solve that. So the same problem that in fact Emil at the very beginning of the session discovered and mentioned is a problem for any sort of system that is hierarchical, very hierarchical, and it has sparse. Because then you would need a kind of representation that keeps track of where you were, the sub-goals, what were things, and the eigenoptions that we were discussing at Kim's tutorial are one of the ways to solve this. That has been proposed, but that's not the only way. There are many ways. If you're interested in this, it's a very thriving field in deep learning, and I feel like just the heuristics of this room with very simple examples has touched upon that problem already. So if you want to look more into that, ask me for more references.
Isn't it always going to be better to have more samples and more replay steps?
Oh, tell me when it won't be. Think about a science fiction scenario where it won't be. If the world changes a lot, then having 1,000 episodes and randomly taking 50 of them, although they are exponentially recency weighted, by the way, might be not optimal, right? So this is good for environments where you can plan, and that assumes a certain stability and low volatility. I'm getting a lot of signals that I should wrap up. So thank you guys. We covered a lot more than I thought we would, and the questions were really awesome. And if you want to continue, come talk to me afterwards. I'm here until the end.